Hi folks, welcome back. This is part 2. So let's take a look at what I asked you to do in the first video. I asked you to consider how you could use the major characteristics of y equals x to help you determine what y equals 1 over x should look like and what characteristics it should have. Okay, so I do want to mention at this point here that eventually we're going to determine, more analytical ways of solving the problems or answering these questions. But for now, I really want us to rely on our intuition. I want us to really see if we can figure out why what's happening is happening. Okay, so let's start with the x-intercept of y equals x. So x-intercepts are important in functions. Let's see if they can help us determine what happens with the reciprocal function. So if the y value here, if I take x equals 0, okay, and I take the reciprocal of that, okay, what do I get? I get 1 over 0, something that's undefined. So I shouldn't expect 1 over x to have a y value at 0, which of course, we already had an idea that it didn't. So if I know that at 0 there's no y value. Let's take a look at what's happening near 0. Okay, so let's say I approach 0 from the right-hand side. Let's take a look at what the y values are doing. Excuse me. The y values are getting smaller and smaller and smaller. They're getting closer to 0. So what happens when I take the reciprocal of, say, 1/2? Well, I get 2. If I get even closer, if I take the reciprocal of 1 over 10, I get 10. Let's get really, really, really close. What happens when I take the reciprocal of 1 million? Well, sorry, if I take the reciprocal of 1 over a million, well, I get a million. So as I get closer and closer to 0, what are the y values of this function doing? They're getting larger and larger and larger. So that makes sense that I should have, this asymptotic behavior as I get closer and closer to 0. Okay, let's see what happens on the left. Okay, my x values are still getting closer and closer to 0, except they're getting larger, they're increasing. So what happens when I take the reciprocal of 1/2, or sorry, negative 1/2, I get negative 2. But then when I take the reciprocal of negative 1 over 10, so I get even closer, I'm going to get negative 10. And we see that these numbers are getting smaller. If I take the reciprocal of negative 1 over a million, what do I get? Negative 1 million. Okay, so as I get closer and closer to 0 from the left, we see that my function is going to be approaching negative infinity. Okay, hence justifying why we have this asymptote and why we have this behavior towards positive infinity on the right and negative infinity on the left. Okay, so we see that while the 0 itself provided us with not much information other than the fact that it wasn't going to have a y value there, looking near the x-intercept gave us some information on the behavior of the function. Okay, let's move on to the end behavior of y equals x. So what's happening as x approaches positive infinity, y approaches positive infinity. Okay, what's going to happen with 1 over x? So say when x is equal to 100, what happens? The reciprocal is going to be 1 over 100. Okay, let's say I take a million. What happens as I take the reciprocal? I'm going to get 1 over a million. And here I realize that as the x's get larger and larger and larger, 1 over x is going to get smaller and smaller and smaller. It's never actually going to reach 0, but it's going to get closer and closer and closer, hence justifying this idea of having a horizontal asymptote. Now similarly on the other side, if I take smaller and smaller numbers, so if I take negative 100 and I take the reciprocal, I get negative 1 over 100. A very small number, or sorry, number very close to 0, but now on the negative side. If I take negative a million, something way far down, what happens when I take the reciprocal? I get negative 1 over a million. Okay, so something that's very close to 0, but it's going to be on the negative side. So it makes sense to have this end behavior again approaching 0 without ever touching it, except now approaching from the negative side. Okay. The question is what happens in between here? Okay. Maybe we can find a point that's of particular interest. So the other thing that I'm asking you to consider here is, do they share any points in common? Okay. So let's try to think. Is there a value whose reciprocal is equal to the original number? Okay, so if you take 2 and you take the reciprocal, you get 1 over 2, not the same. And hopefully you realize that, hey, wait a minute, if I take the reciprocal of 1, I just get 1 over 1, which is still 1. So that means that at this point here, where the y value is equal to 1, the reciprocal will also be equal to 1. So they're going to share this point in common. It's what we call an invariant point, that even if I take the reciprocal, it stays the same. So from here, we get the idea that we're going to have this sort of behavior, which is exactly what we expect for 1 over x. Okay, but that's not the only invariant value. Okay, there's another number whose reciprocal is equal to itself. What if I take the reciprocal of negative 1? 1 over negative 1 is still equal to negative 1. So at this y value of negative 1, it will also be the same, hence giving us this behavior here, which is exactly what we expect. And we get a function that looks very much like the one that you're used to. Okay, so let's try to make a list of things that we look for. Okay, you're going to look for zeros of your original function f at x, and then what did we do? We explored the behavior of the reciprocal on either side. Okay, explore behavior of the reciprocal 1 over f at x, okay, on either side of the 0. Okay, in this case here, we were able to determine that on one side it should be approaching positive infinity, on the other side it should be approaching negative infinity. The next thing we looked at is to use the end behavior of f, in this case here that it was approaching positive infinity, so when we take the reciprocal, we knew that it was going to be approaching 0. Okay, of f, sorry about that, f at x, to determine the end behavior of 1 over f at x. Okay, and the other thing that seemed to be useful was to look for invariant points. But this is where you ask yourself, when is a number equal to its reciprocal? Well, when it's either equal to 1 or negative 1. Okay, so the invariant points, the ones that don't change, occur when f at x is equal to positive or negative 1. Okay, because if I take the reciprocal of 1, I still get 1. If I take the reciprocal of negative 1, I still get negative 1. Okay, so what I want you to do now, okay, is I want you to investigate some other reciprocal functions that are a little more complex than the ones we just saw. Okay, but what I want you to start by doing is I'm going to give you a function f, sketch that graph. Then on that same function, I want you to graph the reciprocal. You're going to see that g is going to be the reciprocal of that function. Okay, and what I want you to do to graph the reciprocal function is look at the three things we looked at in this one here. You're going to focus on the 0. You're going to focus on the end behavior of f, okay, and see if you can determine where a function and its reciprocal should have common points. And when you're done, check your work on a graphing calculator to see if you got it right. Okay, so we'll be back with part 3.